So, thinking about machine learning and economics, or machine learning and econometrics, or machine learning and social science, we can start by saying, what are we talking about here with machine learning? There's two big types of machine learning. There's actually lots of types of machine learning beyond this, like reinforcement learning and different parts of AI. But two really big types for distinguishing for what the comments I'm going to make today are between supervised and unsupervised machine learning. So unsupervised machine learning is like when you have a bunch of videos, or you have a bunch of pictures, or a bunch of documents, and there's no labels on them. Nobody has said that's a cat, that's a dog to start with. Your input is just a bunch of objects. And what you're trying to do is put those into groups that are similar in some way. So they might be, images, and then when you put them into groups, you look at group number 5476, and that group, when you open up all the images in that group, you see that they're all cats. So then you'd say, my machine learning algorithm discovered cats. What it actually did is it put a bunch of images together that it thought were similar, and then later on you looked at it and you said, that looks like cats. But you didn't tell the algorithm that cats existed, or that there was any specific reason to be looking for cats. That's just something that was discovered. There's little difference across disciplines with how these methods are used or what their purpose is. They're generally a first step towards something else. That something else can differ. It could be that you're going to use it as an explanatory variable in a regression, or it could be you're going to use it to describe features of products. There's many different things you might do with it afterwards. But when it's done in this kind of isolated way, I feel like if you want to learn how to do this, you can just Google it, find some great videos, find something on Coursera. And if you're a social scientist, you can just apply the methods. And I don't have anything new to say to you about how to do them. They're going to be similar. I would say that political science is used text quite a bit, and so some methods will get more popular in some discipline than others. But fundamentally, there's not a difference in the goals. The place where things get, I think, a little bit more interesting, or where things that seem alike actually turn out to be different, is in supervised machine learning, which is the thing that sort of looks like running regressions, which is something that we do a lot of in the social sciences, and we teach a lot of in econometrics class. So in supervised learning, you start with a setting where there's independent observations and a stable environment. So, each observation is exchangeable with another observation. And in the simplest case, there's no correlation between them. So a regression problem that we all teach in first year econometrics, we're trying to build a model of the conditional mean, the expectation of y as a function of x. And supervised machine learning is also about predicting y as a function of x. So those basically look like the same thing. And classification, where in this case y would be discrete, so y is maybe a label, like is it a cat, a dog, or a horse? That's trying to understand, which label is most appropriate given x's. That looks like a multinomial logistic regression, which is also something that we teach and study and use a lot in social sciences. So it looks like supervised machine learning is the same thing as what we do in social sciences. And to make them seem even more similar, when you take a machine learning course, probably the first prediction model you learn is regression. And probably the first classification model you learn is, logistic regression. So this all sounds like we're solving exactly the same problem. But then what's kind of funny about it is that we do these things differently. And so I want to kind of talk to you a little bit about why we approach that same problem in different ways, and actually why it's meaningful to ask different questions from those same methods. So just to start with, though, let's kind of take a look at an example of classification of one of the most common problems that's been studied in machine learning, and one of the biggest successes from the last 15 years is our improvement in the ability to solve classification problems. So typical classification problem is, you have a bunch of pictures, say pictures of animals, these pictures you downloaded from the web, and what you're trying to do is to classify them. So that in the classification problem, you're starting with a training data set where there you have images and there you have labels. So people have in your training data set, the data set you're using to estimate your model, you have labels, the Ys, like cat, dog, horse, and you have the pictures. In order to build this classification model, there's some processing you have to do. So first of all, you have to translate the image into observable characteristics of the image. And just a simple way to think about that is like on your computer screen you're staring at right now, you can make an image of me talking to you or my slides using, red, green, blue, and the brightness of each of those colors. And that together will create an image. So that's one way you can translate an image just into, bits and bytes. They're the pixels, each of the pixels, and then for red, green, blue, how bright they are. And now I've got a digital description of the image. Then I want to put that into a model and classify, given X, is this a cat? Now, already there's a little bit of a gap because in some machine learning applications, you're not actually trying to build a model that gives a probability of a cat. You just want to say, is it a cat? So when these algorithms work in production, they're not necessarily spitting out a probability. They might be, they might not be. They might just be spitting out cat, dog, cat, dog. And it might actually take additional computation for it to spit out a probability. Well, if we were studying this problem in economics, we would be building a logistic regression and trying to use that to come up with a probability. And actually, the way that we use the regression in economics would typically be that we would be interested in the coefficients. We would be interested in the function itself. And we would be trying to understand if I changed something, if I changed an X, how would that change the probability? So we would be really trying to understand the model rather than just spit out, is it a cat or is it a dog? Now, some of the big advances for images, neural nets turned out to work really well. And who knew that would be the case, but they are a very rich functional form. And so what the advances in machine learning have been all about is figuring out how to solve this hard problem where you have all these bits that are representing pixels, and I'm going to somehow get a meaningful prediction out of that. And the neural nets can be thought of as a very flexible functional form to do that. So here's an example of like why machine learning is great. This is a marketing brochure for McKinsey. And so in this marketing brochure, the problem was to predict which customers would churn. And that means to abandon a service. And we have on the x-axis and y-axis of this, we have two drivers of churn. And you can imagine that might be, how often you've logged into the website, or some other behavior, but could be a characteristic of a person. So these are the X variables that could be used to predict churn. And so the McKinsey is in this picture contrasting a churn model based on a simple old-fashioned logistic regression. So in the logistic regression, they've got a binary outcome, churn or no churn, and they have these characteristics of the consumers. And they're using those characteristics to predict churn. And this nice smooth green line is the isoprobability line for, so everybody along, all the drivers A, drivers B pairs along that line have the same probability of churn. And so McKinsey's pointing out that in these hand-tuned simple functional forms that people would write down by hand, you would have a very simple relationship between drivers A and drivers B in terms of predicting churn. Now, all these fancy hills and valleys are what come out of the machine learning model. So, and I'm going to assume that McKinsey ran the software correctly, and so that McKinsey's model did a better job classifying churn than the simple logistic regression model. So that's good, and let's assume that's true. And then we can also assume that it's true that this kind of complicated relationship between A and B in terms of prediction was actually better at predicting outcomes in a test set. Let's imagine that's true. But how would you do as a social scientist or even as a business person trying to use this output to make decisions? So if you took this literally, if you held drivers A at 80 and increased drivers B, what this model seems to be telling you, if you interpret it that way, is that if you held drivers A fixed and you increase drivers B, that the probability of churn would go up and then down and up and then down and up and then down. So you have all these hills and valleys in the probability. So if you went out and tried to think about making decisions based on that, you might get some counterintuitive results, and it might not be the best guide about, which customers to recruit, and it might also not be that convincing on mechanisms. So you think, why is that? Well, part of the thing is the goal of a predictive model is just to predict. It was estimated and trained, the shape of the functional form was all about just getting the Y right, getting the best prediction of whether you're going to churn or not. And that's different from a causal analysis, where I might want to say, well, what if B is something I can affect? Like, what if I could get people to log into the website more? Well, would I want to try to get people to log in the website more? Do I think that would actually cause them to churn less? That's a very different question, and you would estimate the model very differently to answer that question. And so one of the insights in the recorded lectures will go into much more detail about is, when you could or couldn't interpret a model in terms of causality, in terms of what you might want to manipulate, or even in terms of who you might want to target for something. And so there's different objectives for different kinds of questions, and actually your estimation techniques should differ depending on the question you're asking. To think about this another way, we could use this model to try to predict who should we call, who should get a phone call. Now, the McKinsey model is going to be very good at figuring out who's likely to quit, but maybe some of those people are quitting your service because they graduated and they're moving away. Maybe they're graduating from Stanford and they're going to move to a different country, or they're going to move to a different city. So calling people who are going to move away is not going to be very beneficial for a company. So that's thinking at a higher level. If you were trying to use a prediction model, predicting who's going to quit isn't the same as finding the people for whom you should intervene. Those are different questions, and you would use different models to answer them. So that's really going to be one set of themes that we're going to want you to learn from this class. If you go to an econometrics class, they're going to assume you're trying to understand, what happens if I hold everything fixed and I change one variable, because that's one of the ways we think about regression. Well, if you go to machine learning class, they're going to assume that you want to predict or you want to classify. And so the objectives are actually different. Machine learning is great. It can fit these complex shapes. So my friend who was at Microsoft made this goodness of fit for Clippy the paperclip, who was Microsoft's first AI. And Clippy didn't work very well, sadly. It was not a very good AI. But we can use AI to fit Clippy's shape. And finally, 15 or 20 years later, we actually have help assistants that actually do help us, unlike poor little Clippy who was made fun of. So just to put a little more structure on the comments I made earlier, and again, this will be elaborated on further in the additional recorded lectures this week. But when we think about prediction, the goal of prediction is going to be to estimate a single number. What is if it's Y, what is my best prediction of Y? And I'm going to do that to try to minimize the mean squared error in a new data set where only X is observed. So the stated problem of machine learning is that I have a data set with Y's and X's. I build a model. If you give me new X's, I can predict it. I can predict what the Y will be. So if you think about it from a professor's perspective, I could hire a research assistant, give them some X's and Y's, and tell them to go back and build a model. And then in my office, I'm going to hide some data, and I know the X's and I know the Y's. When the research assistant comes back, I'll give them the X's, and I'll test them on how well they can predict the Y's. And all I need to know, I don't need to know how the research assistant did it. I don't care if they built a neural net or a random forest or something else. I just care that I'm gonna just give you a pop quiz. I'm gonna feed in the X's, and you're gonna tell me the Y's, and I'm gonna score you just based on those Y's, nothing else. Okay. And so the machine learning problem is actually then a sort of a simple problem because I don't care what you did or why it works. I just care that it works. And if the actual way I want to use the model is, again, to give it more X's and have it predict more Y's, all I care is that it works. So it's kind of machine learning you can think of as like a robotic research assistant. I used to go tell my research assistant to run 100 regressions. Now I've got a robotic research assistant, and they're going to run 1 billion regressions. And they're going to come back with the best one, and I'll be able to tell right away if they did a good job. Okay, so that's what machine learning is good at. Now there's some details, like it turns out that minimizing mean squared error is going to actually entail a bias variance trade-off, and it's always going to accept some bias. So that's a different objective than trying to get an unbiased estimate of the conditional mean function. The idea of how these machine learning algorithms work is you consider a family of models, and you use the data to select among the models, and the common approach is cross-validation. So it's like to prepare for your big test, you pretend that you're studying for a test, you hide some of the data from yourself and see how well you do. And so then you give yourself a bunch of pop quizzes, simulating the scenario that you will later face in my office, and you find the thing that does best in your little pop quizzes that you're giving to yourself, where you hide some data from yourself. You figure out the thing that works best. Once you've got that all sorted out, then you come to my office and I give you the final test and see how well you did. But if you practiced well and simulated the testing environment, you will probably have found something that will also work well in the test set that I hid from you. And machine learning basically works well because you can accurately evaluate performance without a lot of additional assumptions. All you have to see is how well it fits, because its only goal is to fit. You don't have to argue about additional assumptions. Yeah, you could argue about whether the environment you're going to apply it in is actually stable. Maybe it's going to change over time. There's a few things to argue about. And of course, you can argue a lot about whether the algorithms are fair or biased or have some societal implication. But just, do they work? Not much to argue about. So I'm going to do a little bit of provocative discussion here. And I should say, I consider myself a machine learning person. So I can make fun of both economists and machine learning because I publish in both journals and go to both conferences. So I can make fun of both sides. I'm going to say, what do we say versus what do we do coming from the machine learning perspective? Machine learning basically says machine learning is everything. And actually, we probably invented it, I think, right? Nobody ever did anything before machine learning was a thing. So I've been told many times by machine learning folks that if economists had anything to say about how I use data, somebody would have told me. It would have showed up in my machine learning class. And I've been asked even, do economists use data? I thought they did theory. So there's a little bit of a lack of appreciation for the fact that many disciplines, political science and economics and biostatistics and so on, have been grappling with statistical problems for decades and even centuries, and have had some ideas along the way that are helpful for solving certain kinds of problems. Machine learning often, though, will use the language of answering questions or solving problems, even when they are not answering questions or solving problems. So it's very common, and I see this a lot with startups. A startup will come to me and say, I have software for prioritizing customers. Like the churn example I gave. I have software that will help you prioritize which people should get a sales call to prevent them from churning. I'd say, great. Let's see your prioritization software. And what they'll show me is a model for predicting churn. But again, as we previously discussed, being able to predict who's going to quit is not the same as determining who should your salespeople call. Half the people who are most predictably going to quit might be people who are moving away and are not at all affected by a sales call. So they'll say, I've got this great AI algorithm that will prioritize your consumers for you. But in fact, this great AI algorithm is actually just prediction, and it's predicting the wrong thing. It's not predicting the thing you would want for prioritization. Now, it could be helpful for prioritization, because certainly predicting people who are not going to quit means those people probably shouldn't get a sales call. But among the people who might quit, you need something else to figure out who should you actually call. For whom would a call be effective? That's a causal question. And so people in social sciences are very used to thinking about, well, gee, do you even have data that could possibly answer that question? We spend tons of time thinking about, is your question even answerable? And that's not the type of thinking that you're taught in a basic machine learning class. You just assume every question is answerable. And you just need good algorithms. Add a few layers to your neural net, and I'm sure the problem is now solvable. That's kind of the mentality that you get from, especially introductory or basic machine learning. So basically what we say is we can do everything, and we've solved most problems. We have a great hammer and everything is a nail. And that's sort of true, like as a general purpose technology, like prediction is incredibly applicable, and you can have the same algorithms that can be used across lots of domains. So that's actually really important for economics, actually, like big picture economics. Like it's a general purpose technology, and it can be used really widely, and we can make algorithms open source, and they can affect a lot of the world. So I'm a big believer in that, and I give entire lectures on that. But it's not true that just off the shelf that every question is best answered using just those tools. And that's where there's a big divergence between social scientists and machine learning. So generally what machine learning people actually do is they use predictive models. They ignore other questions, whether it's causality, equilibrium, feedback effects. And then they have, little conferences or subfields that sit around and wonder or worry about interpretability, reliability, robustness, fairness. But they have little ways to ask algorithms to optimize for it. And a lot of times, a lot of the literature on fairness is viewed as like an ex post thing. I'm going to verify that my algorithms are fair, or I'm going to put constraints on them, rather than actually completely changing the way you think about them. And which would be, I think, more of a social science approach. So traditional econometrics, economists often focus on the case with a lot more observations and covariates. Every one of you who made it through your first year econometrics or courses had to probably memorize the proof for your final exam that OLS is blue. I still have the little sticky note sticking out of my econometrics textbook for the page with the proof for OLS is blue. So what does that mean? For those of you who haven't had to take that final exam, that means that ordinary least squares is the best linear, unbiased estimator of the coefficients of a linear prediction model. Okay, so ordinary least squares is trying to be unbiased. Now, when I studied that proof and dutifully passed my exams and got an A, without ever really contemplating deeply why I wanted things to be unbiased. The way it was presented, it was just, of course, that's what you want. Why would you want anything else? Why would you want something biased? Whereas in machine learning, when you're trying to do prediction in a test set with a model that might be very rich relative to the size of your data set, you explicitly allow for bias because there's a bias variance trade-off in predictions. And the lectures this week will go into that in substantially more detail. But to start to even see where that breaks apart, if you have more parameters than you have observations, it's obvious that OLS is not going to be good at anything. It's going to be overfit. Economists instead worry about estimating causal effects and what's called identification. Identification means if I had an infinite amount of data, could I answer my question? And just to think of an example where you might not be able to, consider the problem of hotels. So a causal question about hotels might be, if I raise the price of my hotels, how many customers will I lose? That's a business question. And it's something that we study a lot in economics and in marketing. What happens if I change a price? Now, I might go out and collect data. I could collect data. I could scrape prices from, hotels.com or something like that. I could figure out what prices were. And I could hire a research assistant to stand outside a hotel and count the people coming in and out, once a week or something like that, right? So then I could put together a data set that had quantities and prices in it. Okay. And then I could try to build some kind of a model. I could run a regression. Price, quantities on the left side, prices on the right side. Now, what would the coefficient be on prices in that regression? Well, if you ever have gone to a conference or stayed in a hotel, had a school vacation, you would probably realize that actually when the prices are high for the hotel, it's probably full. So you would get a positive coefficient in that regression. High prices, high quantities. And indeed, if your goal was prediction, suppose my goal was for some reason I wanted to guess how many people were in the hotel on a particular day, high prices is a great signal that that hotel is full. From a predictive perspective, high prices predict high quantities. That's a fact. True in the data, absolutely true. And by the way, this is true for a lot of data sets. This is why economists started worrying about this, because in many data sets, prices and quantities are actually positively correlated. So where's the breakdown here? Well, the causal question is, what if I hold everything fixed and I change the price? But you never had in your data a chance where somebody ran an experiment on prices. If you did, you may not know about it in your data. And so in your data, the variation is coming from holidays and conferences and, too many weddings that weekend, other things that increase both demand and supply. And thus, that induces this correlation in the data between prices and quantities. But that doesn't mean if you intervene and raise price that you will sell more hotel rooms. So economists think about that all the time, and they might, if they ended up finding a way to figure out how to estimate this relationship, it's probably true that their predictive model would have very low explanatory power, because the biggest thing for predicting quantities is knowing the price. High prices, high quantities. If you're trying to predict, that's going to explain most things. But if you're looking for natural experiments in price, where price changed for a reason that didn't have to do with a holiday, you're probably not going to have very many of those price changes, and you're not going to have a very good ability to predict quantities, but you will learn more about what happens when you change price. And that's what economists and social scientists really focus on: counterfactual predictions, separating correlation from causality. We also obsess on standard errors because it's actually really hard to learn causal effects. And it's very common that something you find is actually not that well pinned down, and your coefficients could be due to sampling variation. So causal effects, we spend a lot of time worrying about sampling variation. It's also the case that it's very hard to tell if you got the right answer because it depends. So you really want theory to be playing a role, and you want to think about the statistical properties of your estimators. So those are things economists worry about. And we also are very aware that identification problems can't be evaluated just using a holdout set. So if prices and quantities are positively correlated in my whole data set, if I take a random sample, prices and quantities will also be positively correlated in my test set. And I'm not going to figure out from a test set that I misunderstood why prices and quantities were positively correlated. The test set isn't going to do that. In some of my research, and I'll talk about this at the end, we construct very specially constructed test sets that can actually help you understand whether you got the answer right. But it's not just a random sample of the data that's going to fix your problem for you. So, of course, I can also make fun of econometrics, what we say versus what we do. What we say is that we do causal inference and counterfactuals. We think about the data generating process. And we say the God of economics gave us the model, and we pretend that we just estimated one model. We say, the God of economics told me that log of wages depends on the log of something else and something else squared and something else cubed. Now, and we then report causal estimates and appropriate standard errors, plus a few additional specifications for robustness. Now, what we actually do is we go and tell our research assistants to run 100 different specifications just to make sure it doesn't change our results. And then we kind of pick 5 representative ones and we show them and we produce them as if we hadn't done that at all. Now, it's not that we're all bad people. I mean, maybe we are, but it's not necessarily true that we're all bad people for doing it that way. Instead, we're working with what we have, if you like, and we didn't really have a good way to try to do this robustness systematically. And of course, you don't want to publish a result which goes away if you add in a cubic term. So you want to be sure that you're accurately representing the way the world works, because people are going to use your results for policy. So one of the things that machine learning can do is it can take us out of that conundrum. It can give us a way to do robustness systematically, fully describe honestly what we did, and still be able to report results about the parameters we care about. And that's going to be one of the things we'll teach about in this course, how we do that, how we get rid of that very uncomfortable, unpleasant, and unreliable part of research where we just run a bunch of specifications and hope we've been comprehensive enough and hope we haven't been so comprehensive that we've screwed up and gone data fishing for our favorite result. So some key lessons for econometrics. Many problems can be decomposed into predictive and causal parts. And one of the things we're going to show is that once you do that decomposition, then you can use off-the-shelf machine learning for some of the predictive parts. We also want to learn from machine learning how to do data-driven model selection, but we want to do it a little differently. We want to be tailored to our econometric goals, tailored to parameter estimation. And there's some insights, things like, cross-fitting that come up once we tailor our estimation for our goal. And we also might use different optimization criteria, different objective functions, depending on our goal. And we're gonna modify things in a way that optimizes for a specific objective, like parameter estimation, and retains the ability to do inference. Machine learning inspired approaches for robustness, another thing we can learn. Validation. Machine learning always has a test set. I've worked on some of my historical research about auctions had that kind of setting where I had 2 different auction models and I estimated using one auction game and predicted in another auction game. But that's been relatively rare in economics. And so one of the things that I've been working on in my own work is how to come up with clever ways to what types of data sets to look at and ways to define test sets that help us assess better whether we've done a good job with counterfactuals. And some of that's in supermarket data where we have lots of price changes. We've also can learn other computational approaches, even for structural models. Things like stochastic gradient descent are really powerful computational techniques that can unlock a lot of performance in structural models. And I'll talk more about it at the end of the course. So prediction in 5 years, a lot of these techniques will be standard in social sciences. And honestly, they already are becoming a standard. They're becoming a requirement, not an option. Regularization and data-driven model selection will be standard. Prediction problems, the part where you really do just care about a prediction, it will be better appreciated and better delineated from causal models. Measurement using machine learning techniques might be an important subfield. Textual analysis will get bigger. And again, it's already very big in some parts of economics and political science. We'll be better and more careful about explicitly distinguishing causal parts and predictive parts of models. And then we'll delegate the parts that are more predictive to machine learning and data-driven fit. We're going to have reduced emphasis on sampling variation and more on model robustness. And we may consider models with lots of latent variables or factor models more commonly for panel data or different types of data structures that are not just single shot independent observations. Okay,